My name is Eddie Roberts of LERA Consulting Structural Engineers, and I will present the new Charles Library at Temple University. The 225,000 square foot building had a $170 million budget. We began the design in 2014 and completed construction documents in March of 2016 when the project was issued for bid. Then in July of 2016, the project was rebid. The project opened for the fall semester of 2019. This was no ordinary rebid. The structural design of the building changed from almost all concrete to almost all steel. The design team achieved a substantial redesign of the structure and accomplished it in a fast-paced 3 months. To understand how we did it, it's helpful to understand the architectural concept and how we approached the innovative design. The new Charles Library was imagined by the architect, Snowetta, to be very different from the traditional library. The university considers the library as the new focal point to the campus. The heavy stone facade of the exterior reinforces this importance. The building is a literal cornerstone to the future of the campus. The interior space is fluidly shaped with multi-story openings that visually interconnect and allow for visitors to easily navigate the library. In concept, the architect developed two very different concepts. A long-span gateway arch, emphasizing the project as a portal to the university, and a long cantilever structure over a courtyard. We developed structural solutions for each, most notably with structure that inhabited the architectural spaces. Somewhat to our surprise, moving into full design, the architect elected to combine both concepts into one. The design has elements of both the arch, now interior to the building, and the long cantilevers. Under the canopies, the building entrances are set back considerably. The dome canopies are supported by 45-foot long cantilever trusses. The structural systems transfer loads from one set of column grids to the other. More than 40% of the columns transfer in the building, either by deep transfer girders, as sloping columns, or by long span trusses. A large 4-floor terrace cantilevers beyond the building's footprint. A sloping roof wraps over the building. All of the available roof space is green roof, one of the largest in the state and part of the plan aiming for LEED Gold certification.
Most of the library's 1.8 million books are in a large 3-story tall concrete structure, where the books are stored in high-density shelving, weighing 2,700 psf on the basement slab. The automatic storage system uses robots to retrieve books from stacked bins. The truss in here cantilevers 100 feet along the western face of the building. The cantilever trusses are designed for disproportionate collapse. To meet this criteria, each cantilever truss is interconnected to other trusses. Long spanning trusses span over the domed openings as long as 100 feet. The largest of the steel members is a built-up I section, 60 inch in depth with 3 inch thick flanges. The portion of the library's collection that is more traditional is at the top of the building at the 4th floor. The open library stacks weigh 160 psf.
The building was originally envisioned and designed as a concrete structure with some steel. But when the design of the building was complete and issued for bid, the local construction market was very active. The bids from the concrete contractors far exceeded the predictions of the cost estimators. The structural design required a comprehensive redesign from a mostly concrete building to a building that was mostly steel. To still meet the opening date, there remained a 3-month window to reissue for bid. This was a substantial undertaking. To span over the 3-story atrium, a series of leaning columns and A-frame type structures were used. We highlighted the various gravity load transfers and their load paths that required lateral transfers through the building. For example, of the 4th floor diaphragm, shown here. Early on, we extrapolated and predicted concrete floor framing solutions for our heavy library type loading. We also provide solutions in steel, but architectural aesthetics and early cost estimates pushed for a concrete floor system. We focused on the detailing choices. The cantilevered portions of the building are steel, with members logically orientated. The bottom chords of the trusses carry lateral wind loads from the facade and are orientated with webs horizontal. The top chords of the truss carry occupant loads and are orientated with webs vertical. We detailed complex intersections thoughtfully, with connections that eliminate cross-grain tension. When the decision was made to change the building from mostly concrete to mostly steel, we hit the ground running. Our philosophies in detailing and our understanding of load paths, coupled with our innovative use of digital tools, enabled for a rapid redesign. With the change to steel framing, each floor now has a deeper structure. MEP and architectural ceiling requirements need extensive and timely coordination. We introduced an approach of exporting the Revit model to SketchUp and Rhino softwares, breaking down the building to each floor and focusing on possible coordination solutions. We took a proactive role in suggesting new duct locations where the previous locations were no longer viable. For example, with our help, emergency smoke exhaust systems, which are large mechanical systems, were located amid the trusses. Roof exhausts for these systems were smartly located in the folds of the roof structure. The mechanical equipment is hung within an otherwise unoccupiable space. After the redesign, some portions of the building remained in concrete. Most of the lateral system remained as concrete shear walls, in part because of the relatively thin profile the concrete allows compared to equivalent steel brace systems. To maintain the schedule and to allow for steel erection to precede the concrete shear walls, we provided embedded steel posts detailed to receive the steel framing. Sometimes, as shown here, the irregular shape of the walls resulted in steel posts following unusual geometry. The design team overcame the challenges of maintaining the pace of construction to help step in when the CM unexpectedly departed, all while retuning the structure for the redesigned building. The structural design's innovation allowed for the architect's vision to become reality. A transformed structural design, led by LERA, enabled the project to achieve the goals of the university and the design team.